Hi students, today I am going to explain molecular orbital theory applications to solve the questions in NEET and JEE exams. The applications are mainly bond order, stability of molecule, magnetic properties. Mainly molecular theory explains the combination of atoms resulted molecules. So atom plus atom resulted molecule, it means atomic orbitals combined with another atom atomic orbitals resulted molecular orbitals. These molecular orbitals are two types. One is the bonding molecular orbitals and anti-bonding molecular orbitals. Bonding molecular orbitals I indicated with BMO. Anti-bonding molecular orbitals I indicated with ABMO. If you combine two atomic orbitals, resulted two molecular orbitals. So the resulted molecules are two types, mainly combination of atom, nature of combination of atoms. The same atom combination resulted homoatomic molecules, for example N2, H2 and O2, F2 and so on. If atom combination is different, it means two atoms are different, then resulted molecule is heteroatomic molecules. That is, example is CO, NO and CN and so on. To understand the applications of these molecules like bond order, stability of molecule and magnetic properties, we have to learn electron configuration in molecular orbitals. So what I gave the example here, H2, N2, O2, CO, NO, CN, these are all atom combinations having atomic number less than 10. So 1s, 2s, 2p, these orbital electron configuration is sufficient to understand the molecular electron configuration. So s orbital maximum electron capacity is 2 and p, it has px, py, pz, 3 suborbitals. Its maximum filling electron capacity is 6. So s orbital always forms sigma bonds, and p orbital, one of the p orbital involves in sigma bond and remaining two orbitals involves in pi bond formation. Right, let's move on to the electron configuration in molecular orbitals. Just simply we can understand and we can easily write the electron configuration. First of all, the combination of two atoms, right? So first atom atomic orbitals 1s, 2s and 2p, and remaining 1s, 2s, 2p. Right, in molecular orbitals, one is bonding molecular orbital, one is anti-bonding molecular orbital. Just anti-bonding orbital, molecular orbital represented by star or indicated by star. The star molecular orbitals are all anti-bonding, without star all bonding molecular orbitals. Here you see 1s, 2s and 2p. These 5 are bonding molecular orbitals, 1s star, 2s star, and these 2p star indicated orbitals are anti-bonding molecular orbitals. In this electron configuration, we have two patterns. One is up to 14 electrons or below 14 electrons, and one is above 14 electrons. So molecule contains suppose 14 electrons, we have to follow this electron configuration. Suppose molecule contain more than 14 electrons, we have to follow this electron configuration. You see the up to 14 electron, the first 4 orbitals are same for every molecule electron configuration, and the p orbital only different. If you see the p orbitals are 3, just I make it a triangle. Another anti-bonding molecular orbitals I make it as a triangle. So these bottom two are degeneracy, means equal energy. That's why 2px, 2py in bottom stage, and 2pz is in single. So 2p pi 2py, pi 2px, pi 2px, pi 2py, and sigma 2pz. As it is, you write this triangle also indicated with a star. These are anti-bonding molecular orbitals. This is a bonding molecular orbital. If you go to next level, above 14 electrons, the first 4 orbital electron configuration same, and only difference the first as I shown in the 14 up to 14 electron, the triangle in same direction. In above 14 electron, the triangle is in reverse direction. So 2pz, the bottom, 2px, 2py in upper stage, right? And the remaining anti-bonding orbital is the same. Just this small change, you remember, it is very easy to write the electron configuration. So move on to the next application, the bond order. So bond order is equal to number of bonding molecular orbital electrons minus number of anti-bonding electrons by 2. The 2 indicates 2 electrons required for a bond formation. So let us look into example nitrogen. So nitrogen having 14 nitrogen molecule. So nitrogen molecule formed by 2 nitrogen atoms. So 7 plus 7, 14 electrons. As it is up to 14 electrons, as we know the electron configuration, so just first 4 is same and the remaining p orbitals in make it 2 triangles, and just write down the 2px, 2py, 2pz and x star 2py star 2pz star, and fill the electrons to just each orbital 2 electrons, then 2px 2 electron, 2py 2 electron, 2pz. So totally how many? 7 pairs. So 7 pairs equals to 14 electrons. So bonding electrons are 1 2 3 4 5 pairs, 10 electrons. Antibonding 2 pairs, which is indicated by star, 4 electrons divided by 2, it equals to 3. So the bond order in between nitrogen atom is 3. In electron configuration there is no single electrons, it is in a diamagnetic nature. And then move on to the next example, oxygen molecule. Oxygen molecule is a combination of 2 oxygen atoms, so 8 plus 8, 16 electrons. Just above 14 electrons, the below triangle just make it reverse and then fill the electrons. So bonding pairs 1 2 3 4 5, so 10 electrons. Anti-bonding 2 plus 2 and 2 single electrons, total 6 is equals to, the bond order is 2, and that there is a 2 single electrons, it is in a paramagnetic in nature. So based on bond order we can also determine the bond strength of the molecule and bond length of the molecule. And next easy trick for bond order, no need to write molecular electron configuration, electronic configuration. Just you take a baseline, the border line is a 14 equals to bond order 3. So then you just from baseline to top you just decrease 0.5 bond order, or from baseline to down you decrease bond order 0.5 with according to molecular electrons. So 15 16 like this, and above 13 12 like this. And stability of molecule, the last application is the stability of molecules. More bond order, so more stable. So and another point, more electrons in anti-bonding molecular orbital, so it's a less stable, right? So for example, look at in first example, n2 minus, n2 has 14 electrons, n2 minus 15 electrons. If you see 14 electrons bond order how much? 3, and 15 electrons bond order 2.5. so more bond order is n2 molecule, so 3, so it is a more stable. And more electrons in anti-bonding molecular orbital are less stable. If you see helium molecule and helium plus molecule, helium molecule it has 2 bonding and 2 anti-bonding, helium plus 3 electrons, right? So bonding in 2, anti-bonding is only 1. So 1 electron is less anti-bonding molecular orbital electron, so it is more stable. So helium plus more stable than helium molecule. And otherwise another way you can also check the stability. So n2 has 14 electrons, n2 15 electrons. So up to 14 electrons the bonding electrons are more. If goes to 15 16 17 like this, the anti-bonding electrons also increases, so stability almost decreases. So through bond order you can also explain, and this kind of molecules you can see the anti-bonding molecular orbital electrons. Based on that you just answer the stability of molecule. So thank you for watching. Please subscribe and like the videos. Thank you.